So recently we looked at subspaces. In particular, we looked at null spaces. Null spaces. We said a null space is basically solutions, all the solutions to the homogeneous equation AX equals 0. We're going to go into column spaces next. Column spaces. What is the definition of a column space? So let's say you have a matrix. That's m by n. So let's say you have a matrix capital A, and it's of the form first column A1, second column A2, and so on and so forth. The nth column AN. Let A be an m by n matrix the column space of A is what we want to define the column space. Column space of A. The notation for that, denoted COL, so it's a capital C, and then a lowercase o, a lowercase l, of A. The col of A, column space of A, is the span of the columns. The span of the set of columns of A. So the set containing A1, A2, and so on. AN. So it's the span of that set. Right, those columns are just vectors. So that is, in other words, col of A, the column space of A, is defined to be equal to the span of the set containing the vectors A1 through AN. Yeah, so it's just a linear combination of the columns of A. Literally, that's what the column space is. It's all the linear combinations of the columns of A. Okay. So here's an important result. The column space, I mean, we're calling it a space, right? Column space. It's a subspace. It's a theorem. Column space of A, col of A, is a subspace. Now let's actually prove this. So the statement's going to go if A is an m by n matrix, then the col of A, column space of A, that is a subspace of Rm, is a subspace. Rm. All right, let's prove that. We're going to use the subspace test. Right, so remember with the subspace test, so first of all, we want to think about where does this guy live? Where does this guy live? No, we're not even going to talk about that. We're not even going to talk about where it lives. We can just say, let's start off. It's an if-then statement, right? So we're going to assume the part after the if. It's called the antecedent. So we'll assume the antecedent. Suppose A is an m by n matrix. By definition, with, let's say capital A has n columns, right? We know it has n columns. It's an m by n matrix, so with columns 1, 2 through n, A1, A2 through AN. Okay, so that's the form of the matrix with columns 1 through n. And so let's note that these columns are each in Rm. Note that column 1, vector 1, column 2, vector 2, and so on, vector n. These are each in Rm. Why are they in Rm? Why are they in Rm? Well, they're in Rm because This is an M by N matrix. So you have M entries going down each of those columns. So if each of those columns has M entries, they're in Rm. Now, so note that the span of A1, A2 through AN, right? This is how the column space is defined, right? The span is the column space. So the span is equal to the column space of A. That's just by definition. But remember, we said that the span of a set of vectors is a subspace of the underlying vector space from which the vectors come from. Where are the vectors coming from? They're coming from Rm, all right? If you look at A1, A2, AN, they're coming from Rm. So that means column space of A is a subspace of Rm. That's it. That's the proof, right? We proved earlier in one of the previous videos that when you have a bunch of vectors, the span of those vectors, the span of that set of vectors, is a subspace of the underlying vector space, which in this case is Rm for those particular vectors, A1 through A. Right, that's it. So easy proof. Building on previous work that we had done in the past. So it's a subspace, the column space. Just all the linear combinations of the columns. That's all it is, linear combinations of the columns. Here's another interesting result. So here's another way to think about the column space. In addition to thinking of it as all linear combinations of the columns of A, or the span of A, here's another way to think about it. Important theorem. Column space is range. What do I mean by range? I mean outputs. Range of A. Now I draw a diagram later that illustrates this. So let's say here's the statement, if A is an n by n matrix, then the column space of A, which I write col of A. So we said it was the span of the columns of A, but here's another way to write it. It's the set of all vectors B in Rm, such that A times U equals B for some U in Rn. So the column space is all the vectors B in Rm, such that A times some other vector U in Rn is equal to B. Let's prove that. Proof. So here we're going to suppose A is an m by n matrix. Suppose A is an m by n matrix with A having n columns. So let's say A consists of A1, that's the first column, A2, that's the second column, AN, that's the last column, right? We have n columns, and each column is going to have m entries going down. So by definition, the column space of A, col of A, is equal to the span of the columns, right? The span of the set of columns A1, A2 through AN. So what is the span? It's the linear combinations, right? It's all the linear combinations. So I can write this is equal to the set of all vectors B and Rm such that U1 A1 plus U2 A2 plus dot 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 UN AN equals B for some UJs in the real numbers. Now what am I saying here? So what is the span? What is the span? Get a highlighter. The span consists of all linear combinations of the AJs, right? The span is the linear combinations of the AJs. Now this is exactly what I have right here, right? I have linear combination of the AJs, right? I have U1A1, U2A2, UNAN, and I'm just calling those linear combinations B's. They're called vectors B, of the form B, right? So every vector B that can be written as a linear combination of the AJs is the same thing as being in the span, right? Now, what's that? Let's rewrite this now. This is a set of all vectors B and Rm such that A times U equals B. And this is for some vector U in R n. So, in the, let's make this equation green here. Oops, nope, don't want to do that. Oops, don't want to do that. Let's make it green. Nope, don't want to do that. How do we do this? Come on. Come on, dude, work. Okay, let's make it green. Highlight it green. Not that difficult. So this green guy right here, this is just called the vector equation form, right? That's called a vector equation form. So I converted that vector equation form to a matrix vector equation form. So those are actually the same equations. Now, when I said for some uj earlier, for some uj, that's talking about the particular coefficients, right? The particular coefficients. And here, when I talk about, in this next part, for some vector u in Rn, so that vector u consists of entries u1, u2, un. That's all that vector u is, right? It's u1, u2 through un, going down a column. All right, so that's pretty much it. We got it. We got exactly what we wanted, right? We got the column space is equal to all the vectors B in Rm such that AU equals B. That's it. That's the proof. Put a little box to indicate I'm done proving that result. End of proof. So let's try to think about what this is saying. The column space consists of all vectors B such that AU equals B for some U in Rn. So we said that the matrix is kind of like a function, right? The matrix is like a function. It's m by n, right? So over here, I'm going to have my set called Rn, right? And over here, I'm going to have my set called Rm. So off to the side, let's say I take matrix A, it's m by n, and I plug in a green vector. Let's call it u. U has to be n by 1, right? So over here we have the u's. These are all u's over here, right? They're in Rn. They have to be n by 1, right? They have to match this inner dimension. So what A does, it's going to send these vectors u. Let me highlight this over here. Let me highlight this. It's going to send every single vector in Rn, every single vector u in Rn, over here to Rm. Now, what the outcome there is, if you think about it, let's do it in yellow. It's going to be, what, an m by 1. We call that b. The output is an m by 1, right? When the inner dimensions agree, the output is an m by 1. So that's over there in Rm. Actually, I should have different color. But yeah, I'll use yellow. Yellow's good. So over here is what we get called the range. So this is the range, or the column space, right? The column space. Sometimes it's actually called the range. So that's everything over here. All the vectors b. Well, let me get rid of that. That's not pretty. But these are called the outputs of the function, the range. Okay, so these are the b's over here. Well, I'll put them in black, maybe. So they're actually a subspace, right? They're a subspace of Rm. We can see here that the range, right? The range, the column space, is a subspace of Rm. It's a vector space that lives inside of Rm, and that's what we said earlier, right? Where do we say that? Column space is a subspace of Rm. Yeah, we said. So that's the idea.